Imagine you are riding a high-speed train and you drop a ball. From your perspective inside the carriage, gravity behaves exactly as expected. The ball drops in a perfectly straight vertical line right down to the floor. But if I am standing on the platform watching from the outside, the ball is also moving forward at 150 miles per hour with the train. From out here, I don't see a straight drop at all. I see the ball trace a long, sweeping arc. Both observations are accurate from their respective viewpoints. Because human perception of motion is entirely relative, we cannot rely on our eyes alone to build complex machines or launch rockets. We need a universal set of rules. That starts with defining exactly how we measure a journey. In the real world, you might wander through a chaotic, winding path to get from point A to point B. That total path traveled is your distance, but the strict, straight-line gap between your start and end points is your exact displacement. When physicists build their models, they largely ignore the messy, physical journey. They rely solely on this uncompromising, straight-line displacement vector. Mastering motion requires stepping outside our subjective, everyday observations. To calculate how things actually move, we have to ground ourselves in geometric truth. Once we have that precise displacement, straight-line motion boils down to three variables: an object's position, its velocity, and its acceleration. This graph maps the physical movement of an object directly into visual geometry. By plotting position against time, a curving line here clearly represents an object speeding up or slowing down as seconds tick by. To find out how fast that object is moving at any specific second, we look at the exact steepness of this curve. Calculating the slope of the position line at a given point gives us the exact velocity. We can apply that exact same geometric rule a second time. If we look at a velocity time graph, measuring the slope of that line reveals the object's acceleration. You don't always have to draw a graph to find these answers. The standard algebraic equations of motion perform identical predictive work. If an object accelerates at a constant rate, these formulas let you calculate its behavior using pure numbers. Whether you are analyzing the angle of a drawn line or solving a standard equation, you are doing the exact same thing, tracking how fast a rate of change is changing. So if slope gives us acceleration, how do we run the process in reverse? How do we calculate an object's starting position if all we know is its current speed over time? This chart shows a velocity time graph, where the physical 2D space trapped underneath the line is completely shaded. That shaded area perfectly calculates the total displacement. This is the visual equivalent of an integral. Measuring that bounded region elegantly bridges the gap between basic geometry and the complex calculus required to map moving objects. We can apply these rules to a high-stakes scenario: the constant downward acceleration of Earth's gravity acting on an object dropped from an upward-moving vehicle. This diagram outlines a hot air balloon rising steadily 60 meters above the ground. If a passenger drops a stone, that stone doesn't immediately fall. It initially shares the balloon's upward velocity, actively battling the downward pull of gravity before it can begin its descent. By carefully isolating the starting height, the initial upward speed, and the downward pull of gravity, we can plug these parameters into our algebraic equations to reveal the exact millisecond the stone will hit the Earth. These formulas and shaded graphs are tangible tools, explicitly designed to freeze reality and dissect the complex physical forces acting on an object at any given moment. We can now bring this mathematical framework back to that moving train. Using kinematics, we can mathematically prove that the passenger dropping the ball and the observer watching from the platform are both entirely correct. This diagram compares the positions of two observers, A and B, against a stationary origin point, O. This establishes relative velocity, the principle that speed is a strict relationship defined entirely by the anchor point of the person watching. The varying perspectives are simply mathematical variables. By isolating the velocity of the train and the velocity of the ball, we can subtract the vectors from one another to find the objective truth of the motion. Understanding this dual language of algebra and visual geometry gives us a profound advantage over human intuition. Once you establish an object's current position, its velocity, and a strict frame of reference, you transition from observing the present to calculating the future. Physics is an exact predictive engine that allows us to mathematically master reality.